So chapter 2 is all about sets. Did you have an opportunity to read through section 2.1 for today? Would have been a good idea. But let me ask you this. What is a set? When we say the word set in this class, what are we talking about? It's a group, okay? A group of what?
Specific items.
A group of specific items. Okay, great. So when we talk about a set, when we speak of a set, we speak of a collection of things. But the weird thing is, and this is where people begin to get confused if you haven't thought about sets in kind of this formal, logical, mathematical way before, is that a set is at once a collection of things and a thing in and of itself. So you all have Postits with your name on them. You're all part now of a set that we call students in this Math 105 section. Okay? All of you are students in this Math 105 section, and so you belong to that set. You are all elements of that set. Okay? But that set itself is also an object that we can speak of. Right? We can attach properties to that set. The set of students taking Math 105, taking this Math 105 section this semester, are all students at BSU. For example, I just attached a property that applies to the entire set of you. So keeping that straight in your mind, that there are things that we can say about the individual elements of a set and things that we can say about the entire set taken together, and those two things are not always the same. So here's the objectives. The objectives for today is to make that distinction, that clear distinction between a set, which is a collection of things, a collection of elements, and the individual elements themselves. If you can keep that straight, you've won about half the battle. Second, we're going to look at 3 different methods that we can use to describe a set. One of them, which happens to be my favorite, is to describe a set in words, as we've already done. The set of all students taking this section of Math 105. But we'll also use roster notation, which is nothing more than a list of all the elements in the set. And then finally, the one that looks the most cryptic, set builder notation, which is a way of using variables and symbols, mathematical symbols, to express what it means to belong to a certain set. And then we'll use another piece of notation to express membership. Now, when I say membership, here's what I mean. Membership is the relationship between an element and the set to which it belongs. So, for example, membership, set membership, is the relationship between Jonathan, for example, and the set which consists of everybody who's enrolled in this section. Right? It's a membership relationship of an element to the set to which it belongs. So we'll use a piece of notation to do that. Here's a distinction that is also important to keep in your mind, the distinction between a set and its cardinal number. A cardinal number of a set is a number that just counts the number of elements. So taking a look around the room real quick, what would be the cardinal number of the set which consists of everybody in this class? So there's difference between speaking of a set and speaking of the number of elements that that set contains. That number is called the cardinal number and is always a number, but a set is not always a number. A set is a collection of elements. So to have that distinction clear is something we're going to want to do. And finally, and this is really something that throws people for a loop when they see it for the first time, in math we make a distinction between sets which are equivalent and sets which are equal. And we're going to make that distinction today as well. That they are similar notions in that one actually implies the other, but not vice versa. And they're different because in one case we're talking about comparing the elements of two sets, and in the other case we're talking about comparing the cardinal numbers of those two sets. So here's the objectives. It looks like a lot, but I think we can get meaningfully to all 5 of these things before we leave the hour today with the activity we're about to do. And then I guess this little thing is just my encouragement that sets are a key construct. That's why they get an entire chapter in our text. And if you can get to the point where you're able to clearly and logically and critically think about sets and their elements, especially if you keep the distinctions on this slide straight from one another, then I can personally guarantee you that you'll have more success in both mathematical and logical reasoning. So your Phil 111 class will also go better for you if this set stuff is working on your side. So here's what I want you to do with your Post-its. Up here on the screen, I have drawn a set. And I've expressed this set in words. So that's the first way we express what a set is. C here is the set of all BSU commuter students. All right, so with your Post-its, take a moment and come up to the screen and place your Post-it where it belongs on this diagram. If you're a commuter student, you know where to put it. If you're not, put it somewhere else. Cool. So here we have the set which consists of all BSU commuters. I've written it in words up here, and I've given it a name. The C down here is the name that we might give it in notation. By the way, mathematicians at some point decided that capital letters are usually what we use to refer to sets when we use notation. So whenever you write the name of a set, or whenever you see a capital letter, you at least have an idea that that capital letter probably stands for a set. So this is the first way to describe this set. But now that all of you have placed your Post-its up here, now we have some more information about which of you have membership in this set and which of you do not. So Chris, for example, is Post-its in the set. So Chris is an element. I'm going to just sort of see if I can do this. That was satisfying. Okay, so Chris is an element in this set. An element in C. And because of that, in the set C, we use notation to express that membership, that belonging. And the notation that we use to replace the English phrase, is an element, is a funny looking symbol. Looks like this. It looks like an E because it stands for the word element. And so we would write that, if we were using notation for it, Chris is an element of set C. So there's notation that we can use to express that idea of membership. On the other hand, Kayla. Kayla's Post-it's not in C. Why not? She's not a commuter student. Right? So Kayla does not belong to this set. She probably belongs to a lot of other sets, but not this one. And so because she doesn't belong to that set, we use a slightly modified version of this symbol. What do you think it looks like? Yeah, just cross it out, right? So we would say Kayla is not an element of C. Written in that fashion. So there's the notation you use to express the membership of an element in its set. Whenever you see that symbol, you should always remember that on the left-hand side of that symbol, you will always have an element, and on the right-hand side, always the name of a set to which it does or does not belong. When we get along into later sections, we're also going to use a similar symbol to compare one set to another set. And keeping those straight will be important. For today, we have this relationship between element and set that we call membership. Okay? It's a sense of belonging, if you like. One other way of expressing this set is by writing down what we call its roster. And the roster of a set is nothing more, just like it would be on a baseball team or whatever. It's a list of all its elements. And so, in this example, let's say I just refine this a little bit. BSU commuter students in our class for a moment, because I don't think I have time to list every single BSU commuter student on the board. But the BSU commuter students in our class, we could write down all the names that we have on the Post-its up here. So Dakota is up here, Chris is up here, Akeisha is up here, Sophie, Jonathan and Rachel. So those are exactly the elements, the members of this set. And the only difference between that list and a roster is one more piece of notation that goes on the outside. It actually takes a little bit of practice to draw correctly. Curly braces. Okay. So the roster notation for a set is nothing more than a list of all of its elements with curly braces around the outside. Now, we don't always have the luxury of being able to write down a roster for a set, because some sets have infinitely many elements. For example, the set of all integers. But for sets which are finite, and especially small and finite, like this one, we can do that. What's the cardinal number of this set? that we're seeing on the board? Yeah, the cardinal number of this set is 6. It's just the number 1, 2, 3, 4, 5, and 6. It's the number of elements that that set has. So again, here's the distinction between the cardinal number of a set, which is a number, and the set itself, which is 6 of you, right? It's the collection of 6 of you in this class. But the number, the cardinal number, is just a number, whereas the set is actually a group of people in this example. Got it? So for the next example, here's the set of all BSU students who have a Friday class. Please come up to the board and move your Post-it if needed. A quick count of the people in here show us that I think the cardinal number now is 11. So the cardinal number of this set, again, I guess we have to qualify that, BSU students in our section who have a Friday class. That cardinal number now is 11, according to the Post-its that you put up on the board. We can write down the roster again. We could list all 11 of the people that belong to this. I'm not going to do that right now. Because I'm interested in talking about set builder notation for a little bit. And set builder notation, like roster notation, is set at the beginning and the end with curly braces. I knew we were missing one. Thank you. And the curly braces are translated into English, as they usually are, as saying that this is now describing the set of something. So it's the set of. But here's where set builder notation starts to look funny. What we're going to do is in the second half of this notation, we're going to write down the conditions for membership. What does it take for something to be an element of this set? And what we had decided on here is that having a Friday class is what we need. So there's my condition of membership. So which elements belong is answered by this second piece of the notation. But I've left a gap here at the beginning because we have to do one more thing in set builder notation. And we separate the first thing from the second thing with a vertical line. A vertical line is often translated in an English sentence as something like such that, because it separates the conditions for membership in a set from the qualifications, from the entire pool of elements that we're selecting from. There are a lot of people in the world that have a Friday class. Who are the people that we care about for this set F? BSU students. And if we qualify that even further, as I wrote up here, BSU students in this class, right, who have a Friday class. And so that universe statement goes at the beginning of set builder notation. BSU students. And I'm writing it in English now, but I'm going to transform this in a second in our section to use a little more notation. Some notation that we've already seen. And here's how I'm going to do that. We've written down BSU students in our section in blue up here. But that's the name of a set. Right? That describes a set. And so if I want to expand this set builder notation a little bit more, what we'll often do is say that this is the set of all elements X. So now we're giving the generic element in a set a name. So generic element. So it's a set of all X which belong to the set of BSU students in our section, such that, and then instead of saying the word they here, now we can replace that with X. This is getting a little sloppy. I'll recopy it in a second. Okay. So the set builder notation for this set might look something like that. And reading it from left to right, we'll say, this is the set of all X, where X is a BSU student in our section, such that X has a Friday class. So it really explicitly spells out, first of all, where are the elements from this set coming from, In this example, they're coming from the set of BSU students in our section. And then, after the vertical line, what are the conditions that make for membership in this set? In this example, X has a Friday class. So one last thing. Here's your logical reasoning connection for the day, your Velociraptor. If F is the set of all BSU students who have a Friday class, then we might attach a property to that entire set. This should say on Friday. Sorry. I don't know why. When I wrote this, I thought today was Thursday. So we might say something like, every BSU student who has a Friday class will be on campus on Friday. Therefore, what can we say for sure about Reed?
He'll be here on Friday.
He'll be here on Friday. Absolutely. How do you know?
Because he has a class on Friday.
Because he has a class on Friday, he belongs to this set. What kind of reasoning was that? It was logical. I agree. But was it inductive reasoning or deductive reasoning?
Deductive.
Deductive reasoning because?
Because you're basing it off of law that you
Exactly. It's deductive reasoning when you take a property that applies to an entire set, like being on campus on Friday applies to this set, and you apply that property to the elements of that set. That's deductive reasoning, and in this case, seems to be valid, right? Reed is going to have to be here on Friday because he belongs to this set. But of course, the other way around need not necessarily happen, because we can see that all the students that are on the board right here take Math 105. We might be tempted to conclude, therefore, that every BSU student who has a Friday class takes Math 105, based on what we see on the board. You're shaking your head, why?
Because only for our class, we have to take account of every student because we don't know.
We can't take account of every student that belongs to the whole set F just based on a few properties that all of you share, right? That was inductive reasoning, and as your logical reasoning professor tells you, inductive reasoning is on its face an invalid form of argument. So deductive is when you apply a set's properties to its individual elements, and that works, right, by definition of a set. Inductive reasoning, the converse, does not always work.